talking about polarity, intermolecular forces, fluid structures, all of that. And what we're doing now is we're putting it all together. So we're putting everything together that we've been learning the last month, right? Month and a half. And we're trying to figure out, how does that affect a molecule's behavior, right? And so this is where intermolecular forces, the application of everything we've been doing, here's where it all comes together. Sorry, I'm keeping an eye on my computer to see what makes it crash. I have my task manager open to see what keeps making it crash. Okay, so attractive forces, those are forces between molecules. Those are London dispersion forces, our dipole-dipole forces, and our hydrogen bonding. So now we're going to talk about solubility. So solubility depends in part on the attractive forces of the solute and the solvent. The solute is the thing there's less of. The solvent is the thing there's more of. So think like sugar in water. The solute would be sugar, the solvent would be water. So there's a universal saying, like dissolves like. Like things dissolve like things. Polar substances dissolve polar substances, right? Non-polar dissolves non-polar. So miscible, that just means, think of it as mixable. It means two things mix with each other, right? And so using our intermolecular forces, if we have a polar molecule, it will dissolve in a polar solvent. So hydrophilic, that just means like water loving. These are polar molecules. Hydrophilic molecules are polar molecules. So anything, these are just some examples of some things that make things polar. Non-polar molecules dissolve in non-polar solvents. Hydrophobic, so water fearing or water hating, right? Hydrophobic. So for example, oil is non-polar, right? Oil is non-polar. Water is polar, so therefore they don't mix. Have you ever been to the gas station? Gasoline is non-polar, and you see like a puddle. I mean, when there's rain, you see a puddle and it's got a sheen on it. It's very shiny. That's because the water and the gasoline or the oil don't mix, right? They are immiscible, not mixable. Or how about that oil spill that's closing all of our beaches right now, right? The oil is non-polar. The water is polar. They don't mix. They're not miscible. Oil is hydrophobic. Water is obviously water, hydrophilic. So many molecules have both hydrophilic, water-loving, hydrophobic, water-fearing parts. And so the solubility becomes a competition between the attraction of the polar groups and the attraction of the non-polar groups. So you know what substance has both pieces? Soap. So think of soap, right? When you get anything on your hands, you use soap. Soap has a piece of it. So here's soap. This is just like a long chain. And then they'll have like a polar part right here. So a bunch of maybe O's. And so if you have something that is polar on your hands, I don't know what you might get that's polar on your hands and it washes off. Or you might have something non-polar like oil on your hands and it washes off, right? So soap has both pieces to it. So we're going to practice with this one. So again, immiscible, that just means not mixable. Not mixable. So pentane, again, these are our long chain carbons, which we've talked about. And these are all H's. And these are all H's here. Okay, just pretend those are supposed to be H's, okay? So pentane is non-polar. Remember, only C's and H's is always non-polar. Water, of course, is polar because it can hydrogen bond. So when you put water in pentane, they don't mix because the attractive forces in water, right, are stronger than the attractive for the pentane forces. So the water molecules kind of like all clump together and the pentane molecules all clump together and therefore they don't mix. We've probably experienced this Have you ever gotten your car like washed at like the gas station, right? And they do the little like fancy wax, maybe not, you know, they spray on the rainbow stuff on your car and you're like, oh yes, it's so pretty. Or you wash your car really nicely and then it rains. And then you're like, what? Seriously? But when it rains after you've got a nice clean car, you'll notice that the water molecules kind of bead, right? They make these like these really pretty cool looking like beads, right? That's because the wax and the soap they use on your car is non-polar. So it puts a non-polar coating on your car, but water is polar. And so when the water touches your car, it kind of balls up and the water molecules are attracted to each other and repelled by the wax. And that's why it makes those nice little beads. Now, it's different if your car is like super dirty and then the water molecule comes on it, you don't see that beading, right? It just kind of like makes streaks. So next time you wash your car, notice it's because the wax is non-polar, the water is polar. Those two are immiscible. They don't mix. All right, so polar solvents or anything, again, polar would be dipole, but dipole. So something that has dipole-dipole forces, or hydrogen bonding, which again, not a bond, just super strong dipole-dipole. So again, water, these are our hydrogen bonds here. I guess it's right here. Not bonds, right? Because they're in between molecules. It's just a super strong intermolecular force. Polar solvents will dissolve or they're miscible with polar molecules. Here's another one. This is the one I have to make for you in lab. Somebody remind me that this is what the Lewis structure looks like here. It's an H. And so the net dipole, if you had to draw a net dipole, would be this way. So this end here would be a little negative, and this end would be a little bit positive. This would be dipole, so dipole, hydrogen bond. All of these are polar solvents. Ethyl alcohol, this is just a bunch of C's with an OH. When you see that OH, so if you see like C, 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 well, this one looks like this, OH. This is what ethyl alcohol, this piece makes it polar, right? If it was all C's and only C's and H's, then it would be nonpolar, right? So this is polar, nonpolar. Remember, only C's and H's is nonpolar. Like, for example, hexane or carbon tetrachloride, right? This is a nonpolar molecule. Only C's and H's is nonpolar. This is nonpolar because there's no lone pairs and everything around it is the same, nonpolar. This is only C's and H's, nonpolar. Right, so this is where we learn to draw our Lewis structures, figure out our bond angles, right? And then our polarity, and then our intermolecular forces. So remember, all these only have London dispersion forces. That's supposed to be net. That's all they've got. Okay, so we've talked about dispersion forces, nonpolar molecules. Well, everyone has dispersion forces, right? Everyone has them because everyone has electrons, but nonpolar molecules only have them because that's all they've got. Polar molecules have dipole-dipole forces and London dispersion, and then hydrogen bonding have hydrogen bonding and of course London dispersion forces. Well, here's another attractive force that we haven't really talked about. It's between an ion and a dipole. Now, remember, an ion is actually positive, cation, or negatively charged. So in a mixture, if you have ions, like from an ionic compound, they're attracted to the dipole of a polar molecule. And the strength of this depends on the solubility of the ionic compound. So for example, when we put salt in water, right? So before, what we said is, I'm gonna put it up here. So when we did like a dissociation, remember when we did dissociation? We said when this dissociated, it became Na plus and Cl minus AQ. So this AQ just means dissolved in water, right? Well, what happens? Like what does that dissolved in water means? Well, what happens is this Na is positive charge, right? It's a cation, it's lost electrons. Well, it is positively charged. So the negative part of our water, right, here's our partial negative, is going to be attracted to that ion. So we call this an ion dipole, right? Because water has a dipole, right? Because it's a polar molecule, right? All molecules have dipoles. Remember, dipoles, just do this again. Dipoles, right? Oxygen's a little bit negative, hydrogen's a little bit positive. So if we were going to draw a dipole, we would draw it like this, right? Meaning this side of the molecule is negative, this side of the molecule is positive, right? So all polar molecules have dipoles. And so we call it an ion dipole because it's an attraction between an ion and a dipole, right? These are stronger than all the rest of the intermolecular forces. Why? Because an ion actually is positively charged. It's not, sodium isn't like a little bit positive. Sodium lost an electron. It is positive, right? Chlorine isn't a little bit negative, right? Like oxygen here is a little bit negative. It's not completely negative. Chlorine is negative. It gained a whole electron, so it is negative. So these ion dipoles are really strong. Of course, not like an ionic or covalent bond strong, but stronger than a hydrogen bond is strong. By the way, when this happens, this AQ here, when we put something in here, do you see this? We call this a sphere of hydration. Sphere of hydration, right? And so because it looks like the water is making a sphere, or in hydration, sphere of water around the ion. And when you put any ionic compound in water, this is what happens. So before we just put like AQ, right? What does that AQ mean? This is what this AQ means. This is what this AQ means. The water is surrounding it. Okay, so let's practice this. All right, so our choice is going to be 1 or 2. 1 or 2. So which one of these is more soluble in water? Okay, so what do you think? 1 or 2 for A? And feel free to type your answer in the chat. And if you don't want everybody to see it, just send it to me, direct message. I'm seeing a bunch of them. I'm waiting for a few more of you. I see you out there. I know you're there. All right, there's a bunch more. Just spill my tea everywhere. All right, so our first one, what we notice is, again, the one that's more soluble is going to be one with the more polar, because water is polar, right? It's got hydrogen bonding. So the one that's more polar is going to be the one that is going to be more soluble. Well, this is hydrogen bonding. This is just a polar molecule. How do I know this is a polar molecule? Because this is only CHs, and then we added some extra stuff. So yes, this is polar, so this is going to be dipole, but this is hydrogen bonding. So this one will be more soluble in water. And now our next one, again, all we see are C's and H's. C's and H's, non-polar. Oh, there's a Cl, that's going to make it polar. So the more polar it is, the more soluble it is in water. Now, if I changed this to CCl4. So if I said, choose a substance in each pair that's more soluble in carbon tetrachloride. Now, carbon tetrachloride, again, looks like this. So you draw this out. I'm not putting my lone pairs in, but now you know they're there. This is nonpolar, right? No lone pairs, all the same elements, nonpolar. So in that case, the one that's less polar would be more soluble. The one that's non-polar would be more soluble, right? Like dissolves like. Polar dissolves polar, non-polar dissolves non-polar. Miscible, that means mixable. immiscible, not mixable. Okay, so let's summarize what we've talked about. So dispersion forces, often we write those LDF because Mr. Fritz London discovered them. London dispersion forces are the weakest, right? All molecules have dispersion forces because all molecules have electrons. So they all have dispersion forces. The magnitude increases with the molar mass because greater molar mass means more electrons. More electrons, stronger dispersion forces. Polar molecules have dipole-dipole, right? So it's a polar molar. Remember the dipole is the little like plus. That's not a very good arrow, right? The negative side of one end attracted to the positive side of the other. That's a dipole force. So polar molecules also have dipole-dipole forces. Hydrogen bonds are the strongest of the intermolecular forces, right? And remember, hydrogen bonds are between O, N, or F, or I always say, oops, F, O, N. So you can remember they're fond. Hydrogen bonding is fond. And again, not a bond, right? And it has to be between HF, HO, or HN. They must be directly attached to the hydrogen. Ion dipole is kind of a special sort of one, right? This is like an ion, which is either positive or negative, either gained or lost electrons, attracted to a dipole. They are the strongest. I guess I said hydrogen bonding is the strongest. It's not really the strongest intermolecular forces of the weaker ones. Ion dipole is kind of like a whole nother class. They're especially important in aqueous solutions. Okay, so let's put these in order so you can kind of see this. So here's the weakest. And here's the strongest. Now, if we were going to add all types of bonding here, our next one would be covalent bonding. Covalent, because they're sharing electrons, and then ionic, right? And so, and there's a big line here, right? Because even these are like 5% of these, right? So these are so much stronger. So this is actual bonding. So covalent share electrons, ionic transfer electrons, right? Great practice for your exam, right? And so which one's stronger? When the transfer of electrons, those are stronger than covalent bonds. So we have dispersion. Again, these have to do with just electrons. Dipole-dipole, these are these polar molecules, right, that have these dipoles. Hydrogen bonding between F, O, and N, it's FON, and an H, right? These are just super strong dipole-dipoles. And then we have ion dipoles, and it's between either a cation and an ion and a dipole, right? Either one of those. And this is what happens when we do a dissociation. So remember at the beginning of the class, we had to in Chem 101, you had to do all these dissociations. This is what was happening, those dissociations. The ions split apart and the water molecules surrounded them in this sphere of hydration. All right, so now we're going to use these. We're going to use these intermolecular forces to predict how things behave on more of a macro level. So we've been talking about, okay, this atom or this molecule is attracted to this molecule because of this reason, but how does that affect life, right? How does it affect what we do in our lab? So we're going to look at this. The first thing we're going to look at is surface tension. So we've all seen surface tension. Have you ever seen like a bug land on water? And you're like, right, the bugs can walk around on water. That's because water has a really high surface tension. So the layer of molecules at the surface behave differently than the layers inside of the solution, or we'll just say water, is because the cohesive forces on the surface have a net pull into the interior. So the surface actually acts like an elastic skin that allows you to like bugs and things to float on the surface. So think of it as this way. So here's water and here's air, right? Air is like nitrogen, oxygen, right? There's a little bit of CO2 in the air, right? Look, nonpolar, nonpolar, nonpolar. Air is nonpolar. All our substances in air are nonpolar, right? But this is water now. What do we know about water? It's polar. Air is nonpolar. Remember, like dissolves like is attracted to like. So what happens when you have water is you have, so here, this is gonna be my surface now. So you have all these water molecules here. These are my water molecules. I'm not a very good drawer, I think we can all admit. And what happens is, these are gonna be water molecules now, okay? They're just gonna look like this. They're attracted here to each other, and then the water molecules that are in the water are also attracted to them. So the ones at the surface, they're being pulled sideways and down. So they're being pulled this way and they're being pulled down. This creates a film on the water because they're being pulled this way and down all at the same time. And it creates, like what we said, like almost like an elastic skin over the water. See, this is probably a better idea. This one looks a little better than what I was doing. So the surface molecules interact with only these neighbors, where these ones have more interaction. So they're being pulled over and down at the same time. So they actually have a higher potential energy. And what, you don't need to know any of these units, by the way. we're just gonna use these to compare intermolecular forces. So the higher or the stronger the intermolecular forces, the higher the surface tension. Okay, so what does that mean? So if you had like a bug that was going to land on water, it can land on water because water has a pretty high surface tension, right? Because it can double hydrogen bond, super strong intermolecular forces. Where this is ethane or benzene, this is actually benzene, which is just, it doesn't matter, it's nonpolar. It's just hydrogen bonding, superpolar. This is nonpolar. Look how much lower its surface tension is, right? So a molecule might not be able to actually land on it, right? Because the surface tension is lower. Stronger intermolecular forces, higher surface tension. Weaker intermolecular forces, lower surface tension. So again, the stronger the intermolecular force is, the higher the surface tension will be. Also, we can kind of mess with surface tension. If we increase the temperature, we can actually decrease the surface tension. And you might have done like an experiment with like water and pennies, maybe in high school or middle school or grade school, and you were actually doing an experiment with surface tension. If we increase the temperature, what happens is those molecules start moving. If the molecules start moving, we start breaking apart those intermolecular forces, right? If the molecules start moving, we start breaking some of these. If we break those, we decrease our surface tension because they don't have that same attraction to each other. So when we make them move, which we do by increasing the temperature, then we can actually break the surface tension. So actually, let's look at a picture. And you, again, might have done this when you were younger. So here's the surface tension. All you need to know is this is low surface tension, high surface tension. This temperature, low temperature, high temperature. So you can see here, our highest surface tension is when it's at the lowest temperature, right? Because the molecules are maximizing those intermolecular forces, right? But when we increase the temperature, here's like 100 degrees, now our surface tension is so much lower because we made those molecules move. And when we make those molecules move, we break those intermolecular forces. So it doesn't have the same pull as it did before, less surface tension. So if you increase the temperature, you decrease the surface tension. Surface tension, because you decrease the intermolecular forces. I shouldn't say decrease, I should say weaken. Because I don't want you to think like we're talking about like changing it from a hydrogen bond or something. So you weaken the intermolecular forces. All right, the next one we're going to look at is viscosity. So viscosity it's an interesting thing. The definition of viscosity is the resistance to flow. Think of honey. Honey is very viscous, means it has a high resistance to flow, right? Honey is very, right? You could turn it upside down and you're like, seriously, come on, 5 minutes, you haven't moved yet? Honey is very viscous. It's the resistance to flow. Now, the larger the molecules, the larger the viscosity. So again, you don't need to know what these units are. We're just going to use them as like comparing. So if we look at how big, here's just a hydrocarbon. Remember, a hydrocarbon, it's just hydrogen carbon. Really long, really big molar mass. Here's our pentane, smaller, less molar mass. Viscosity is higher here than it is here. The bigger the molecule, the larger the molecule, the stronger the intermolecular forces, or I'll just say London dispersion forces, the larger the viscosity. Now remember, viscosity is the resistance to flow, right? So it makes it harder to move. So the larger the molecule is, the greater that molar mass, the more London dispersion forces are, so the harder the molecule is to flow. It doesn't flow as easily. Now, if we take that beyond just London dispersion forces and talk about hydrogen bonding, right? The stronger the intermolecular forces in general, the higher the viscosity is, right? So the higher the intermolecular forces, or the stronger the intermolecular forces, the higher the viscosity. So something that has hydrogen bonding will be more viscous than something that only has London dispersion forces. And this next one, changing temperature again, if we raise the temperature, we will actually reduce the viscosity, which means it has less resistance to flow. And you've probably already done this one, right? Let's say you want honey, and the honey is just not moving. And you're like, I need this honey to move faster. So what do? You heat it up, right? When you heat up the honey, all of a sudden it flows much easier, right? And what we've done when we heat up the honey is we are breaking those intermolecular forces, allowing the molecules to slip past each other and flow more easy. We're decreasing the viscosity. Has anybody done with maple syrup, right? If you leave your maple syrup in the fridge, it like flows and it kind of is like really slow when it flows, right? But have you ever had warm maple syrup? So when it's cold, right, it's maximizing those intermolecular forces. So the molecules aren't allowed to slip by each other because the intermolecular forces are kind of holding them in place. But the second you heat up that maple syrup, you've broken those intermolecular forces, or a lot of them, and now the molecules are free to flow, right? Have you ever accidentally like poured syrup thinking it was going to be cold, like at a restaurant, and it was warm, and then you like dump it all on your pancakes? You're like, too much syrup, right? That's viscosity, right? If we break those intermolecular forces, it becomes less viscous, meaning it has less resistance to flow. So if we increase our temperature, we decrease the viscosity because we break those intermolecular forces. Because when we make those molecules move, then we break or overcome those intermolecular attractions, and therefore now the molecules are free to move. All right, here's an example of viscosity and temperature. So again, you don't need to worry about these units, just this means high, this means so it not flowing. High viscosity, not flowing. Low viscosity. I'm just gonna say low vis, flows easy. So when we have our temperature low, our viscosity is much higher, means its resistance to flow. So if this was honey, our honey would be very viscous. Then we heat up our honey. Maybe not to boiling, but maybe we boil our honey, all of a sudden the viscosity is much lower, right? So it flows easier. So the warmer it is, the lower the viscosity, the more easily it flows. Okay, so that's viscosity and surface tension. Now we're going to talk about capillary action. So capillary action is the ability of a liquid to flow up a thin tube against the influence of gravity. So the narrower the tube, the higher the liquid rises. So it's the result of two forces working in conjunction, cohesive forces and adhesive forces. So cohesive, right? If you're cohesive, it's those coming together. So it's the molecules, intermolecular forces within each other, right? Like a water being attracted to a water. That would be a cohesive force. And then you have the adhesive forces. And this is the attraction between the tube. So here's my water traveling up my tube. The cohesive force is the attraction between the tube and the water, right? So if the tube is polar and the water is polar, they're attracted to each other. That would be an adhesive force, right? The water is adhering to the surface because they have similar intermolecular forces. So here's like the little thin tubes, which they're actually really fun to play with. We won't get to play with them in 219, but they're actually really fun to play with. If you take organic, you play with these all the time. So the adhesive forces pull the liquid up the tube, and the cohesive forces pull the rest of the liquid with it, right? So you can't really see it, but like if this tube was bigger. So, and this is, let me make my water blue. So here's my water, right? So I have these adhesive forces. So here's my water. The adhesive forces are pulling the water up the side, right? But then the cohesive forces of the water are bringing the rest of the water up with it. So it's kind of like it goes up here, and then the rest of it comes with it. So the adhesive forces attract because the glass is polar, water is polar. So the water molecules are attracted to the glass, and then the cohesive forces of the water bring the rest of the water up with it. So the interior, the liquid rises up the tube until gravity counteracts it. And the narrower the tube, the higher it can go because those adhesive forces are greater. And we've actually experienced these adhesive and cohesive forces before. And we do it every time we use a graduated cylinder. Because this actually occurs in a graduated cylinder. So if this is our graduated cylinder, let's make it red. So here's your graduated cylinder. When you look at your graduated cylinder, right? Here's like the divisions on your graduated cylinder. It looks like this, right? This is a meniscus. And the reason it's shaped like this is because there's these adhesive forces between the glass and the water, because the glass is polar and the water is polar. And so they're pulling the water molecules up the side, creating this meniscus. That's why whenever we read the volume, we always read it from the bottom of the meniscus. Right? So this is what we see every time we put anything in our graduated cylinders. So it's this curving of the liquid is, again, a difference between the adhesive and the cohesive forces. Now, what if you put a non-polar liquid in a test tube or in a graduated cylinder, right? So if you had a polar, glass is polar. So if you had a polar side and a non-polar liquid, the non-polar liquid would be like, I don't want to be near you, and try to pull itself away. And you would actually see this little convex, or it's like an anti-meniscus, because what's happening here, let me use a better color you can see. So what's happening here is they're actually repelling each other, right? So because this is non-polar and the side is polar, they're actually repelling each other, right? They're immiscible, even though they're not liquids. And so this could also happen if you had a polar molecule or a polar solvent like water, and you had a plastic graduated cylinder. You wouldn't see this because the plastic is non-polar, right? And so this again is a meniscus. Okay. Now the next thing we're going to talk about is vaporization. I added a couple extra things on here, so you might need to take some more notes. Okay, so vaporization. So we talked about how the molecules at the surface have higher energy. And so they continually escape the liquid, right? And we know this. If you leave, let's say you have a puddle of water. Let's say you spill water in the lab. By the time you come back to the lab next time, the water will be gone because the water continuously vaporizes, right? Or escapes the liquid phase into the gas phase. Now, the larger the surface area, the faster the evaporation. So if you left like a cup of water in lab, like an actual cup of water, when you come back to the next lab, probably still there, right? Maybe not as much water, but the water will still be there. But if you spilled that over the floor, it wouldn't be there because when we increase the surface area, vaporization is faster. So when it becomes a vapor, this means a liquid becoming a gas is a vapor. Now, only some molecules have enough energy to escape the liquid phase. And the higher the temperature, the faster it evaporates. And we know this, right? If you had water and you watered your lawn and it's like 105 degrees out, right? That cement that got watered is dry in like 5 minutes. If you watered your lawn this morning and it's cooler out, right? It might be there for hours, right? So the warmer it is, the faster it evaporates because the molecules have more energy to break those intermolecular forces and escape. Because when we increase the temperature, we break the intermolecular forces and the molecules are free to escape. And so think of it this, I know sometimes this graph is a little confusing. So think of this as the surface, right? At a higher temperature, more molecules can escape. At a lower temperature, less molecules can escape. Because at a higher temperature, more molecules have enough kinetic energy to escape the liquid phase. Increased temperature, increased evaporation. Why? Because we're breaking those intermolecular forces. Okay, so how do these intermolecular forces affect evaporation and condensation? So this is just a little bit of extra pieces on here. So the weaker the intermolecular forces, the less energy it takes to break them, right? The weaker the intermolecular forces. So London dispersion forces are weak, so they're going to be easier to break. Hydrogen bonds are strong. They're going to be harder to break. The weaker forces mean that more molecules can escape that liquid phase, right? Also means that more energy needs to be removed from the vapor phase before they can go back down, right? Because molecules in the vapor phase or the gas phase move like this. Molecules in the liquid phase move like this. So they have to get rid of energy. So once we break those intermolecular forces, it's hard to get them to come back down to a liquid. So the net result is you have more molecules in the vapor phase in a liquid that evaporates faster. So the weaker the intermolecular forces, the faster it evaporates. These molecules that have very weak intermolecular forces are said to be volatile. All right, we already know this one too. When you go to a gas station, what do you smell? Gas, right? Why? Because gasoline, is a non-polar solvent, right? It's a non-polar liquid. It has very weak intermolecular forces. The only thing holding it together are London dispersion forces. They're very weak, easy to break. At room temperature, they all want to break. It's enough energy to make them break. So they turn into gases. That means volatile, something that goes from a liquid to a gas really easy. That's volatile. Think fingernail polish remover. Have you ever been in or walked by a nail salon? Right? Why are they always wearing those masks? Because of all the chemicals they use. They're using volatile chemicals, which means it turns from a liquid to a gas very easily. They have very weak intermolecular forces. Paint thinner. Anybody ever smelled paint thinner before? If you've ever smelled anything, you're like, whoa, right? And it makes you like jump back. That's a volatile liquid, which means it must have very weak intermolecular forces because it's going from the liquid phase to the gas phase very easily because we're breaking those intermolecular forces at a very low temperature. So non-volatile liquids are liquids that don't go from liquid to gas. So they have stronger intermolecular forces. Like, for example, like motor oil. It is London dispersion forces because it's oil, but it's like 40 carbons long. It's huge, it's gargantuan, it's a massive thing. So it's non-volatile. Okay, this brings us to equilibrium. So if we have a closed container, so here's water, and I'm going to close this container. So if we have a closed container and we've got water molecules here, right? The water molecules are going to escape into the gas phase, and then some of them will come back here. So we end up with some in the gas phase and some in the liquid phase because they continually evaporate and condense. Eventually, you end up with the same evaporation and condensing cycle where you end up with actually the same amount in the vapor phase the entire time. And this is called equilibrium. When there's no gain or loss of material, we call that equilibrium. It doesn't mean they're the same. It just means we're not seeing any changes. And if you take Chem 229 next semester, oh, we spend like too long on equilibrium. So this is what equilibrium looks like. So they begin to evaporate, but then some begin to condense, and then eventually the rate ends up being exactly the same. The rate of evaporation equals the rate of condensation, and then we have about the same amount sitting up here. Okay, so that brings us to our next one, which is vapor pressure. So let me go back here. Vapor means gas, right? Pressure is just molecules hitting the side of a container. So these molecules are hitting the side of this container. That is what pressure is. More molecules hitting the side of the container, higher pressure. Less molecules hitting the side of the container, lower pressure. So all vapor pressure means is gas molecules hitting the side of a container. So the pressure exerted by the vapor is called the vapor pressure. And we're going to talk about Dalton's law in a little bit, not quite today though. So the weaker the attractive forces between the molecules, the more molecules that will be in the vapor phase. Okay, so let me just go back to our picture. If it's easy for molecules to escape, meaning if it's easy to escape, they have weak intermolecular forces because they can go from liquid to gas very easily. That means you're going to have more molecules in the vapor phase, right? The easier it is for them to escape, the more molecules we'll have in the gaseous phase. That means the higher the vapor pressure. So the more volatile the liquid is, the higher the vapor pressure is. So the weaker the intermolecular forces, the higher the vapor pressure, because that means the higher vapor pressure means more molecules in the gaseous phase, because it's easier for them to break those intermolecular forces because they're already weak and go and be gases. More gases means more gases hitting the side of the container, higher vapor pressure. Now, vapor pressure versus temperature. If we increase the temperature, again, we break more intermolecular forces, which means more molecules are free to get into the gaseous phase. So if we increase the temperature, we increase the vapor pressure because more molecules can break free of those intermolecular forces. Small changes actually make a pretty big difference. And again, it depends on intermolecular forces. If you've got really strong intermolecular forces, like if you've got a hydrogen bond, it's going to take a lot more energy to break them. So you're going to have to heat it up much higher to make those intermolecular forces break so they can become gases. So let's look at a picture of this. So here's temperature, again, low, high. Here's vapor pressure, low, high. Remember, vapor pressure, high vapor pressure, that just means weak. Oops. I don't want to, high vapor pressure, low vapor pressure. I don't want to confuse these two with what I'm about to write. Put them a different color so they don't combine each other. So a low vapor pressure, right? So if we look at a low vapor pressure, let's just look at our water here. So our water has a very low vapor pressure, so it has strong intermolecular forces, meaning not a lot of molecules escape the gaseous phase, right? Weak intermolecular forces, high vapor pressure. Strong intermolecular forces, that's not enough, low vapor pressure, right? So the stronger the intermolecular forces are, the harder it's going to be to break them, which means less molecules are going to be able to escape into the gas phase. So these are high intermolecular forces. Weak. I'm going to use weak instead of low. IMF. I don't want people to confuse, right? High vapor pressure, weak intermolecular forces. So if we look here, this is atmospheric pressure, right? This is 1 atmosphere. We've talked about this conversion a couple times. So this is like where we live, right? So where we live. And so if our temperature, if we look at water, here's water, boiling water. Here's freezing water. Let's just look at water. From here to, okay, maybe not freezing. Let's just look here, warm water. You can see as we increase the temperature, the vapor pressure increases. So as we increase the temperature, we increase the vapor pressure because it's easier for the molecules to escape. Now, at what we call atmospheric pressure, which means these two, it's about where we live. It's just the pressure at sea level. The normal boiling point is 100 degrees Celsius. And that's true, right? Where we live, the boiling point is indeed about 100 degrees Celsius. But if we look at ethanol at 500, here's its boiling point. Okay, so, oops, let me go back. Let's look at, here's its boiling point. Let's put that in the right place. Look here, here is, where's TI, ether, acetone. This one has weaker intermolecular forces, so it has a lower boiling point. We're going to talk about that one in just a second. Okay, now from looking at this, which one of these looks like the most volatile? Okay, remember, volatile means it goes from a liquid to a gas easily. If it goes from a liquid to a gas easily, that means it has low or weak intermolecular forces. So these are the questions you're going to be running across now. You're not only going to be having to draw Lewis structures to figure out if they're polar or non-polar, then you have to figure out their intermolecular forces and then how they behave, right? So that's why I didn't put this on your next exam. It's going to take us a while to practice with these. Okay. You obviously don't have to draw these, you can just look. All right, so the most volatile, again, this would be the highest. I'll say weak intermolecular forces has high vapor pressure. So the most volatile would be the one with the highest vapor pressure. Why? Because the highest vapor pressure means it's the easiest for it to break. And I know, sorry, some of you guys can't really see these colors. I'll just do it. Here's water. This one you can see, TiCl4. This one is, this one's ether. Ether. This one's acetone is this one. And the green one is chloroform, which isn't even on here. Or ethanol. Here's ethanol. Okay, so which one has the weakest intermolecular forces or highest vapor pressure? This one does, right? It's because at a low temperature, it has a higher vapor pressure, or let's just pick at 20 degrees. It still has a higher vapor pressure, meaning weaker intermolecular forces. Let's do 30 degrees. Again, highest vapor pressure, weakest intermolecular forces, right? High vapor pressure, weak intermolecular forces. Okay, let's try one more. This one, it's the same thing I just wrote. You know what, I'm gonna do the letters here. This is A, there's A, B, C, D, and acetone is this one, E. There you are. Now you can see, because I know some of you guys can't see the colors. Okay, so this is your guess. This is your problem. Try to figure this one out. Which one has the strongest intermolecular forces here? What do you think? Strongest intermolecular forces. I'm seeing a few. I'm waiting for more. Yeah, you're right. B, strongest intermolecular forces, right? Because, well, on these you can see for especially the one with our, kind of have to compare where you can see them all together, right? That's the way to best compare it. So I guess we could compare at 40 degrees because we can see them all. But you can see this one has the lowest vapor pressure. So therefore the lowest vapor pressure, the highest or strongest intermolecular forces. And we look at this, it's even stronger than water. This is just a super, super huge gargantuan molecule. So it actually does overcome hydrogen bonds, right? That's why its London dispersions are so big. Okay, now boiling point. We talked a little bit about boiling point. We'll talk about this next module also. So remember, the normal boiling point is the temperature at which the vapor pressure is the same as atmospheric pressure. So what does that mean? So when the number of molecules, I'm just gonna put a top on this. When the number of molecules above a liquid, remember pressure is just molecules hitting the side of the container. So when the number of molecules above a liquid is the same as outside that boiling point, that's when something boils, right? The lower the external pressure, the lower the boiling point. Okay, so here at the ocean, we're about 1 atmosphere. right? So things boil at about 100 degrees Celsius. But when you go to a mountain, let's go to Mount Everest, just because it's much higher than where we are, sea level. Well, I mean, we're about where Boston is, sea level, right? So therefore, there's less molecules, right? If the pressure is lower, that means there's less molecules outside, right? Because remember, molecules are just things hitting the sides of the container. Well, if there's less things, there's less pressure. Where we are at the point when the number of molecules inside is the same as the molecules outside, water boils at 100 degrees. But on Mount Everest, when the same amount of molecules inside is the same as the number of molecules outside, water boils at 78 degrees. So let's go, here's Mount Whitney or Denver. Let's go to Denver. Everybody knows where Denver is, right? Right, in Denver, it's about a mile high, about 5,000 feet up. Water boils at 94 degrees Celsius. So that means if you cook pasta here, where we live, it takes like what? 6-7 minutes? It's going to take longer if you go to Denver, right? Everything takes longer to cook at higher altitudes because the pressure is lower. Okay. Now, also with boiling point, just a little side note, right? The higher the boiling point, the stronger those intermolecular forces are, right? Higher boiling point, higher intermolecular forces. Why? Because for something to boil, it has to go from a liquid to a gas, right? If it's harder, if they're stronger, if the intermolecular forces are stronger, then it's going to take more energy to break them to go from a liquid to a gas. So the higher the boiling point, and we've talked about these, this also goes with melting point. We've talked about this one a few times, the stronger those intermolecular forces. So the highest boiling point should be the highest intermolecular forces, highest intermolecular forces. There it is. It's going to be TiCl4. And you can actually look here. So 760, that's, here's 760. This is atmospheric pressure. This is at 760 mmHg. That's us here. And you can see its boiling point is going to be higher, right? When it hits that number, it's going to be higher. So here's water, by the way. This one's water. Look, when it crosses this line, it's about 100, right? When water crosses that line, TiCl4 is not going to boil until like 135, right? Ether, it's going to boil at like 35 degrees Celsius, right? So things boil when the pressure inside, the number of molecules inside, matches the number of molecules outside. Okay, the last thing we're going to talk about today are phase changes. So we're going to be going from liquids, solids, gases, and vice versa. So quickly, we're going to talk about the critical point, which is actually pretty cool. So the temperature required to produce a supercritical fluid is called the critical point. And this is like when the line between liquid and gas gets blurred. It's neither a liquid nor a gas. We call it a supercritical fluid. We've never really, probably never talked about that before. The critical pressure, the temperature at that point is called the critical pressure. So the critical temperature, at the critical temperature, or at higher temperatures, the gas can't go back to a liquid no matter how high the pressure gets. We can't make it go back to a liquid. Okay, so with the definition of those two, let's look at these phase diagrams. So phase diagrams often look very similar. They're a little different for every molecule. And you'll see in Chem 101, I even have some for like carbon, I have some crazy phase diagrams. So they always kind of follow the same rule. Temperatures here, low, high temperature, pressures here, low, high pressure. It always starts with a solid, then a liquid, then a gas. These lines are the boundaries between those. So when we go from a liquid to a gas, right? If we go from a liquid to a gas, that's called vaporization. If we go from a gas to a liquid, that's called condensation. If we go from a solid to a liquid, that's called melting. If we go from a liquid to a solid, that's called freezing. So when we melt something, we call it fusion. So melting is called fusion, or freezing, fusion. Here's our vapor pressure curve, right, when we're going from solid to a gas. Now, this one you might not be as familiar with. When you go from a solid straight to a gas, that's sublimation. Think dry ice, go straight from a solid to a gas. Or if you go from a gas to a solid, that's deposition. So have you ever gotten frost on a window? So that's water in the atmosphere going from gaseous water straight to solid water on your windshield. So that's deposition. So you need to make sure you know these definitions. This is the critical point. So just erase these. Do you see how this line is black and dark? So it's the border between the two, but then all of a sudden the line ends and there's no line here. So this is the point where it's like neither liquid nor gas, but sort of both. And at that point, we call it the critical point. This would be the critical temperature. This would be the critical pressure if that line was straight. So here's 1 atmosphere. And so when the pressure reaches 1 atmosphere, that would be our boiling point. So our normal melting point, let me just erase all this really quickly. So our melting point is when melting, right, is going from a solid to a liquid. So here's us at sea level. So when it goes from a solid to a liquid at sea level, that temperature is the melting point. Same thing with boiling point. When something goes from, right, a liquid to a gas, right, at sea level, that is going to be, that temperature is our boiling point. So this is how you read phase diagrams. We're going to practice with these. And so see how this one looks a little different than this one. But again, they all have kind of the same pieces. They always go solid, liquid, gas. It might not look exactly like that, but that's what they do. And again, at 1 atmosphere, if it's turning from a solid to a liquid, that would be the melting point. This would be the boiling point. There's another one here that I want to go over. At this point right here called the triple point, it's both a solid and a liquid and a gas all at the same time. So solid, liquid, gas, all existing at the exact same time. That's called the triple point. And just a reminder, when we're going from a solid to a liquid, we call it fusion, or liquid to solid. When we go from a solid to gas, or gas to solid, we call it the sublimation curve, and the other one's called vaporization curve. Okay, here's another one. So I'm showing you all these different phase diagrams so you can kind of see. So this is specifically water. So water, when it goes from, right, solid, liquid, gas, here's at sea level. So when it goes from a liquid to gas at sea level, that's our boiling point. This would be 100 degrees. Solid to liquid, melting point. So this would be 0 degrees for water. The triple point of water would be this pressure, you'll see would be 0.006 atmospheres. And the temperature would be 0.01 degrees Celsius. And here's the critical point. You see how, like, this is where it ends. And again, if we did this, this would be 374.1 degrees Celsius. And this would be 217.7 atmospheres. So again, that's the point where liquid and gas kind of are interchangeable. So again, just practicing with reading these phase diagrams. Here's that. See, this one shows it really well. See how there's no line here? That's where you can tell your critical point is. So when the line stops, that's your critical point. The triple point is when all three come together. That's your triple point. Just kind of showing you how to read these. So this is water. Here's CO2. So it looks a little different. So here's 1 atmosphere, right? This is our 1 atmosphere here. So remember, something boils when it goes from a liquid to a gas at 1 atmosphere. Well, if you look at this, here's 1 atmosphere. It never goes from a liquid to a gas at 1 atmosphere. So therefore, CO2, as we know, is a gas, right? At any pressure, at our pressure, it's definitely going to be a gas. Same thing with solid to liquid. So to get to solid CO2, you have to go very low in temperature, right? So if you look here, if you go from a solid to a gas, which is the only option we have, the only option we have here is from a solid to a gas, is negative 78.5 degrees Celsius, right? And that's the point we're going to go from a solid to a gas. The triple point where they all meet, where it's solid, liquid, and gas, negative 56 degrees. So this would be negative 57-ish. And this would be 5 atmospheres, which is like 5 times what we are right now. Again, here's the critical point where the line stops. But as you can see, all of these are very, very similar. Okay, so again, this is just, again, a good picture of the critical point. Here's the triple point. All right, you ready to practice this? So last thing we're going to practice. So here is the phase diagram for CO2. What phase is present at each of these conditions? So your answer is either solid, liquid, or gas, or it could be 2. And so here's 1, 2, 3, 4, 5. So I'm going to give you just a minute to practice this and figure out which phase. So you're going to use this to figure out which phase it is at. 1, 2, 3, 4, and 5. All right, so I'm going to give you like a couple minutes to practice this, and then we're going to go over it together in just a couple minutes. Okay, so let's go over these. So our first one, 20 degrees Celsius, which would be down here. And, oops, sorry, up here, 20 degrees Celsius. And about here, maybe here, that would be a liquid, yes. Negative 56.7 degrees Celsius and 5.1 atmospheres. That's everything, right? That's both a solid, a liquid, and a gas. That's the triple point. Triple point. 10 degrees Celsius, here maybe, here, and 1 atmosphere, right? Solid, liquid, gas. That's going to be gas. Negative 78.5 in 1 atmosphere. Oh, there you are. That is going to be straight from a solid to a gas. That's sublimation, right? It's a solid and a gas sublimation. And our last one is 50, which is going to be up here. Sorry, kind of cut that out. In 80 atmospheres, which is like higher than this. That's just going to be, we call it like a supercritical fluid. It's neither a gas nor a fluid. It's kind of both. Supercritical fluid. That was the first piece that I introduced. Okay. Oh, there we are. Supercritical fluid. Great. Okay. So these are our phase diagrams. All right. So that's all for intermolecular forces for us.